This broadcast is made possible by the Capricorn Group. This lesson is provided by Eduvision with the support of sponsors.
Right, grade 11s. We have to carry on with the bonding section that we have started off with yesterday. And we did a new type of bond yesterday. What did we call it?
Coordinate bonds or covalent.
Yeah? Dative covalent. Okay. A coordinate bond or a dative covalent bond. And how does it differ from a normal covalent bond?
For example, H2O will have 3 hydrogen atoms. The one hydrogen atom doesn't have anything, so then it connects.
Okay. We have that when we have two atoms bonding by means of a coordinate bond, the shared electrons are supplied by only one of the components. All right. What do we call that component? It's got a special name. The one that supplies the lone pair of electrons. The ligand. Yes, a ligand. All right. The ligand is the one that supplies the lone pair of electrons. Okay. Now, I've handed out some notes to you at the beginning of the period. And this is the next section that we are going to do. Your book only has a very tiny reference to the shapes of the molecules, and it is actually a very important part of the work. Now, when we started drawing bonding of molecules, for example, if I had hydrogen, I would draw it like that. All right, there's an electron and there's an electron. And the molecule forms a straight line if you drew a line between the nuclei. We will call a molecule like this linear. Linear, all right? All of the diatomic molecules will be linear. Molecules something like hydrogen chloride will also form a linear molecule because there's only two atoms, a hydrogen and a chlorine. Yes, usually it will be a linear molecule. Whether we have a double bond in oxygen or a triple bond like in nitrogen, it doesn't matter. It still forms a line. Okay, so the molecular shape then, just very simply linear, it is the first one on your page. Now, in contrast with this, when we would draw a water molecule, we'd always do it like an upside down Mickey Mouse head. Okay? No, then it's wrong. No, it must be drawn like this. There's a special reason for it. Okay? So a water molecule, we have a hydrogen and a hydrogen bonding onto oxygen, forming the water molecule. That's the oxygen nucleus. We find that the hydrogen atoms are bonded with a specific angle in relation to each other, and we'll look at the explanation of that in a moment. So water is an example of an angular molecule. I'm going to do it in the next, or carbon dioxide I'll show you now in a moment. Okay? When we draw carbon dioxide, because that's actually a very good question, how did I draw it? Yes, next to each other. There's the carbon. I'll show you in a moment. I'll answer that question. Okay, oxygen has got 6. There we go. Yes. This carbon dioxide molecule is linear. Okay, I'll do the explanation in a moment. Then another type of molecule that we can do would be something like ammonia. Okay, and what happens is when we draw ammonia, now it's very difficult to draw it in 3 dimensions. But in actual fact, we have a nitrogen, all right? And then if my hand was the nitrogen atom, the hydrogens form like a tripod foot. All right? With the 3 hydrogens. It's difficult to draw because it's a flat surface, all right? And the molecules are 3-dimensional. But it's got like a tripod, like a triangular foot. Okay? So the ammonia would be an example of a pyramidal. A pyramidal shape. And we'll have a look at those angles in a moment. The last shape that you should be aware of, yes? Yeah, it's a dotted line into or out of the page. Remember the Lewis and the Bohr structures? With the Lewis we can draw a line. Are you with me? Okay, so that is what they've used on the diagrams there. All right, now, the next molecular shape that you must be aware of then is something like methane. And here we find we have a carbon atom and 4 hydrogen atoms. But what it does is, if I had 4 fingers and the carbon atom was here at the top, it makes a foot to stand on. We refer to this shape as tetrahedral. Tetra, 4. Makes a, well, square foot. All right, tetrahedral. It's a what? Yeah. Well, yes, it's got, I'm sorry, it's not got 4 on the foot. All right, yes, yes. I'll explain the shape now when we start with that. Okay, now. There's a definite angle to these atoms when they bond. But what influences this angle in relation to that angle in relation to that angle? And why does this make a linear molecule? All right, now it's got to do with the electron pairs that are available in the outer shells. All right? If I go and have a look at my linear molecules, we find that there is a repulsion between the electron pairs. Remember I said to you, why do electrons pair off? When we draw them with it, yes, they spin in opposite directions, and that is what pulls them close together, so they pair off in 2s. But one pair has a repulsive effect on another pair. So they don't go bumping into each other because they repel each other. Now we find that the strength of the repulsion between the pairs of electrons can differ. We refer to a pair of electrons that forms a chemical bond as a bonding pair. All right? And a pair of electrons like that is not involved in a bond, is known as a single pair. All right? Are you with me? Now, when I have bonding pair repulsion, it is very weak. No, sorry, single pair. Yes, bonding is weak. Sorry, bonding is weak. When I have bonding pair, single pair repulsion, it is slightly, okay? And when I have single pair repulsion, it is, relatively speaking, very strong. Well, here I have a single pair, okay? And there I have a single pair. And this, oh, undo. No. Yes, okay. If I have a single pair, now they go separate. There's a single pair, and there's a single pair. These two repel each other. All right. So they push away. Yes. So they will push away as far as they can in 3 dimensions. Now, here I have a single pair, a bonding pair. This bonding pair is going to be repelled by 1 single pairs, 2 single pairs, 3 single pairs. But yes, it's weaker. So they will push him to one end of the molecule, and that's where it will stay. Do you understand that? But that is easy because we only have 2 atoms. Same thing. Over here we find, well, that single pair, they will repel each other equally. Those 2 will repel each other equally, but they will repel the bonding pairs. But once again, the repulsion on that side is equal to the repulsion on this side. Can you see that? Because those 2 bonding pairs repel those 2 single pairs. And the single pair repulsion is the same over there, pushing them away, but they are repelled, the molecule, as an equal distribution. All right? Yes, they've got the same number of electrons and the ones that they share. Yes. Yes. Okay, I'm first going to explain this one. It is over here. I'll do them in comparison. Now, when we get to water, here we find we have 1 single pair, 2 single pairs, and we have got 2 bonding pairs. Now, the repulsion between bonding is very weak. So they do push each other away, but not very strongly. And then we find the repulsion between these 2 pairs is very strong. So they push each other away as far as possible. All right? Then we have this pair is going to repel that pair, and this pair is going to repel that pair and that pair, slightly weaker than what they repel each other, but stronger than what they repel each other. And it pushes the hydrogen atoms down into an angular molecule. Look at carbon dioxide. On the center atom, we have got 2 bonding pairs and 2 bonding pairs. The repulsion between the bonding pairs is equal. On the oxygen, I have single pair that will repel each other as far as possible, but I have single pair bonding pairs that repel equally. The same thing on that side of the molecule. So there's no resulting force pushing them down. If I had a single pair over there, it would have pushed them. But I don't. You understand? And that is why the carbon dioxide molecule is linear. In a triple bond, there will be 3 bonding pairs. Okay. All right. Let's. Yeah, well, they pair off in general. All the electrons do, whether they're involved in a bond or not. Yeah. That is why they like bonding if they've got 3 open electrons that haven't paired off, because there's repulsion between them. It's an unstable state. All right. Now, when we're going to have a look at ammonia, just have a look. If I go and draw my nitrogen and my hydrogens, okay, there's nitrogen. How many electrons does nitrogen have? 5. 1, 2, 3, 4, 5. Yeah. Altogether 7, but 5 in the outer shell. All right? So here we have our hydrogen atoms. Now, if you go and compare this to the water molecule, can you see we have 2 single pairs that will repel each other strongly. And then these single pairs, when they are pushed away as far as they can from each other, they repel those. All right. Now, if we look at ammonia, we only have 1 single pair, so we don't have the strong single pair repulsion. Do you agree? We have got a slightly weaker single pair, bonding pair repulsion, and the very weak bonding. So they are going to be pushed down. Yes? If it has something like that, that's like water. Yes, it does. It's going to push them down further, because I've got 2 sets of pairs repelling it. Yes, water does. Water's got 2 pairs. 3, that's going to push it down stronger, because they will repel each other stronger. Then we've got 3 pairs repelling fairly strong. You understand? Okay. We're going to have a look at the bond angles in a moment. All right. That is why they differ, because over here the bond angle will be different, because we only have 1 single pair repulsion. They should be slightly bigger, because the force pushing them down is slightly smaller. All right, but sometimes because we have 3 and on the other one we only have 2, it also plays a bit of a role. All right. So the next one then that we have to have a look at is methane. Now methane has a carbon bonded onto a hydrogen, and a hydrogen. This is a 3-dimensional molecule. Carbon only has 4 electrons, and hydrogen only has 1 electron. So what do we know? Is there any single pair repulsion? No. We only have bonding pair repulsion, and they are equal in all directions. So they are going to go in 3-dimensional structures as far away from each other as possible. Yes, and that is why, if you look on the diagram when it's drawn, it's got a foot on the bottom, like that, and 1 sticking up there, like that. Now, that is the tetrahedral shape. So look at the notes with the typing on it. Yes, that one. Molecular shape at the top, linear, the diatomic molecules. The bond angle is going to be 180 degrees, because that angle there is 180 degrees. That's logical. The next one, angular. Now the specific example is that of water. And the hydrogen-oxygen-hydrogen bond over here, this bond, in other words, that angle is equal to 104.5 degrees. Water, yes. You would be able to extend the theory to something with an identical structure. Okay. Yes, yes. All right. Yes, yes, yes. All right, it doesn't matter in which molecule it is. But bonding, single pair. Single pair is very strong, bonding, very weak, and in between bonding, single pair. All right. Then if you're going to have a look at the ammonia molecule, here we find that because we have 3 atoms bonded onto them, the bond angle, and there's only 1 single pair, so it doesn't push them as close. All right? So the angle becomes 107 degrees. And the last one, tetrahedral one, methane, The bond angle is 109.5. I always confuse them. They shouldn't, no. If they do, it can be an unknown compound XY4. Similar formula, it's going to be tetrahedral. All right. Okay. Just a little extension. Water is a polar molecule. It is strongly polar. When we did polar molecules with water, when was that? Grade? Did we do it? Somewhere along the line we did it. Two reasons. The one reason, lots of single pairs on that side. All right, strong repulsion. I have a charge of -4 there. These repel each other less strongly, all right, push down on the one side. Now, also, this nucleus and that nucleus has an attraction on these shared electrons, okay? Oxygen attracts those electrons slightly stronger because it's got a greater positive nuclear charge than what the hydrogen will. Yes, so the whole side of the molecule becomes negative, and this whole side of the molecule has a slight positive charge. Okay? Why can something like methane not be polar? Yes, it's a symmetrical molecule. It's the atoms are distributed equidistant in 3 dimensions. Do you understand? So even though the carbon nucleus will have a stronger attractive force on the shared electrons, it's in all directions, and the molecule can't be polar. Because the moment you have a polar molecule, remember the forces between the particles become stronger. If we go and look at ammonia, here we have ammonia. Can you see that ammonia will be slightly polar? Very slightly. But not as polar as water. All right. Okay, that is the bond angles. Just look at the note. I've tried to sort of explain it because your book doesn't really explain it very well. The question below the molecular shape, why are these bond angles not 90 or 180 degrees as one would expect? The reason is the central atom has electrons in its outer shell grouped together in pairs. Electrons which are shared are known as binding or bonding pairs, while electrons which are not shared form a single or lone pair. The ligand is the one that supplies the single or lone pair. All right. They don't take part in the bond. Then there is a repulsive force between the different pairs of electrons. The repulsion between different pairs differ. Single pair is stronger than single pair, bonding pair. And lastly, bonding pair is the weakest. Huh? It will be similar to ammonia. No, there will be. Remember, in water, we've got let me draw water over here by the ammonia one. No, where are we there? If I have H3O, remember, I've got oxygen, I've got one hydrogen and another hydrogen, and then I have another hydrogen sticking on there, but the water molecule has got 1, 2, 3, 4. Do you understand? Okay, very good if you can see it. There we go. So it's going to look like ammonia if you had to deduce an answer or apply your knowledge to find an answer. What will the shape be? More or less, what would the size of the angle be? Same as ammonia. No. All right. No, just molecular. Ions form a crystal lattice. All right. Okay. The coordinate bond formation at the bottom. Coordinate bonds are formed when both the shared electrons are supplied by one of the atoms involved in the bond. And there I've given you an example of water forming the hydronium ion. Water is the ligand because it supplies the electrons so that a covalent bond can form between the proton and water. and then ammonia to form the ammonium, and lastly the coordinate bond formation on a hemoglobin molecule. Yes. Okay. That's good. Yeah. Okay. All right, rather late than never, maar is reg. Okay, then on the next page that I've handed out, it's just a more, well, a three-dimensional diagram of what the shapes look like. The first one, linear, angular, or bent. They show the single pair of electrons as two smaller little bubbles. Can you see that? All right. And then pyramidal and tetrahedral. You can ignore the trigonal pyramidal. Don't worry about that one. Okay. That, I think, is the end of today's lesson. So
This lesson is provided by Eduvision with the support of sponsors. This broadcast is made possible by the Capricorn Group.
Your Citro Clear dishwashing liquid and Citro Power multi-purpose cleaning liquid is now available in new refill packs. And even better, they're lacquer affordable. And whether you're cleaning at home or at work, while Citro Shine window and surface cleaner keeps everything shiny, Citro Power is a new, powerful surface cleaner for stovetops, fridges, melamine floors, baths, tiles, and more. Available at your nearest retail store, Citro by Also Namibia. Expert cleaning solutions you can always trust.
This lesson is provided by Eduvision with the support of sponsors.
okay, grade 11s. Yesterday, we had a look at the molecular shape, all right, of the different molecules, linear, angular, pyramidal, and tetrahedral, and we had a look at the repulsion between electron pairs, lone pairs, and bonding pairs, bonding, lone pair, all right. And we explained the shape of the molecules. Now, we are still busy with bonding in general. I did mention water, that is a polar molecule. If you look in your textbooks on page 31, they discuss the different structures and the angle on the left-hand column in the block at the top. On the right-hand side, they discuss the water molecule. It has two lone pairs. So the structure of water is similar as it is shown in the table. The structure explains why water was attracted to the charged ruler. We said water is a polar molecule. I said to you yesterday, why is water polar? Because if we look at the bond of oxygen and hydrogen, that's the hydrogen, oxygen, oxygen, we have the electron pair repulsion pushing down the hydrogens at an angle on the one side of the molecule. Yes. But if you go and look at why is oxygen the slight negative side and why is hydrogen the slight positive side, then it has to do with the oxygen molecule has got two lone pairs of electrons. They are negative. So that side of the oxygen molecule is going to be negative. And then I said to you the other reason is because of the attractive force of the nuclei on the shared pair of electrons.